You know those simple lines you see in chemistry drawings, the ones connecting the C's and the O's? Well, they're hiding a pretty cool secret. Today, we're going to pull back the curtain and look at the real, three-dimensional architecture that holds molecules together, especially when they start sharing more than just one pair of electrons.
I mean, have you ever really stopped to think about it? When you see a double bond, is it just two identical bonds stacked up? And a triple bond is just three of the same? Or is there something, I don't know, a little more elegant going on underneath? Well, that's exactly the mystery we're going to solve today.
All right, let's jump right in. Our first big clue that something is up is how these bonds behave. A single carbon-carbon bond, it acts like a simple axle. The atoms on either end can spin around freely, no problem. But a double bond? No way. It's completely rigid. It's like taking two wooden planks and gluing them flat against each other. You can't twist that without breaking the whole thing. So the big question is, why?
To understand that, we kind of have to become molecular architects. And it turns out that all multiple bonds, I don't care if they're double or triple, they're all built from just two fundamental types of building materials.
Okay, so building material number one is the sigma bond. You can think of this as the main structural frame of the molecule. It's the strongest link, and it's formed when orbitals overlap directly, head-on, right along the line connecting the two atoms. Every single covalent bond that exists, single, double, or triple, starts with one of these sigma bonds. It's the foundation.
So, if we've got our sigma frame in place, how do we build up to a double bond? To see how it works, let's look at our first case study, a really common molecule called ethene.
In ethene, each carbon atom does this really neat thing where it blends some of its orbitals to create a flat triangular arrangement. But here's the kicker. After making that flat sigma bond frame, each carbon atom is left with one untouched p orbital, and it's sticking straight up and down, totally perpendicular to the rest of the molecule. And since these two p orbitals on neighboring carbons are parallel and close, they can overlap too, but not head-on. They overlap side by side.
And that side-by-side overlap creates our second building material, the pi bond. This is the reinforcement. It's what makes the bond stronger. It actually forms two regions of electrons, one cloud above the sigma bond and one cloud below it. This pi bond is the glue that holds those two planks from our analogy together.
So here's the big payoff. If you wanted to rotate the atoms around that double bond, you would literally have to twist and break that side-by-side pi bond overlap. And that takes a ton of energy. This is it. This is why a double bond locks the molecule into a flat, rigid shape. The architecture itself dictates how it functions. It's so cool.
Okay, so if one pi bond acts as a reinforcement and makes a bond rigid, what do you think happens when we add a second one? Well, that brings us to the triple bond, and our perfect example here is acetylene.
Now in acetylene, the carbons use a slightly different mix of orbitals that makes everything arrange in a perfectly straight line. And this time, it leaves not one but two untouched p orbitals on each carbon. So what you end up with is the central sigma bond frame and then two completely separate pi bonds that form around it, one going up and down and the other going front to back.
With these reinforcements on two different planes, the molecule is basically locked into an even more restricted shape, a perfect straight line. So again, you see this pattern. The number and type of bonds are telling us exactly what the molecule's 3D geometry has to be.
Okay, so far so good. Our blueprints have been really clear. The pi bond reinforcements have a very specific place to go. But you know, chemistry loves to keep things interesting. Let's look at a really fascinating case where the blueprint itself seems, well, flexible. Let's talk about benzene.
Seriously, think about that for a second. What if a molecule could arrange its pi bonds in more than one perfectly valid way? Which structure would it actually choose, or does it even have to choose at all?
So take benzene. It's a 6-carbon ring. We could totally draw a valid structure for it with alternating double and single bonds, just like this. Looks perfect.
But wait, we could just as easily draw it like this, with all the double bonds shifted over one position. Both of these drawings follow all the rules. They're both totally legitimate. So which one is the real benzene? The answer is neither.
Yeah. The reality is, neither drawing is 100% right. It's not like the electrons are rapidly jumping back and forth between these two options. No, they're doing something way more profound. What's really happening is a phenomenon called delocalization. Instead of being stuck in 3 specific pi bonds, those 6 pi electrons are actually smeared out and shared equally by all 6 carbon atoms in the ring. You can picture it as two continuous, donut-shaped clouds of electrons, one above the ring and one below. And this act of sharing, of spreading out the load, it makes the whole structure incredibly stable.
So wow, we've gone from looking at simple lines on a page to this whole dynamic 3D architecture of frames, reinforcements, and these weird delocalized clouds. But why is understanding all this so important?
Let's just boil it down to the absolute must-knows. First, all multiple bonds are just a simple combo, one sigma bond frame plus 1 or 2 pi bond reinforcements. Second, it's those pi bonds that are the key to molecular shape, locking them into rigid, flat, or linear structures. And finally, sometimes, like in the case of resonance, those pi electrons can get spread out over the whole molecule, which we call delocalization, and this creates some seriously stable molecules.
This model has given us an absolutely powerful architectural blueprint for molecules. But that whole idea of delocalization in benzene, it kind of hints at something even deeper, doesn't it? It begs the question, what happens when we stop thinking about electrons as belonging to individual bonds and instead start thinking of them as belonging to the entire molecule all at once? Now that's a story for another time, and trust me, it's a fascinating one.